Hey chemistry students, this is Mr. Resentes. I'm on page 125 and we're taking notes. Now this template is on Edline. You're welcome to print it out if you're having a hard time reading it, or you could try and keep up with me, but you should be able to find this on Edline. What we're going to do is we're going to continue with the atomic model in chapter 3. Remember in chapter 2 in chapter 4. Remember in chapter 3 we were carrying on about how the structure of the atom was developing over time. Well, we haven't developed it completely because we still don't know all of the details regarding the electron. So that's what we're going to talk about here in chapter 4, unit 3. We're going to talk about the structure of the atom with regard to the electron specifically. Well, the atomic model continued. One of the things that you have to remember is that light behaves both like a wave and a particle. So before we get started, you have to understand what a wave is. I don't think you have a problem understanding what a particle is, because we deal with particles quite frequently. The way they bump into one another and etc. is something that we're familiar with. A wave, on the other hand, a lot like a wave on an ocean, we're a little bit less familiar with. So let's go through some of the characteristics of a wave. The first characteristic of a wave is amplitude. Amplitude is the distance from the center of a wave to the crest or trough. Alright? So what I mean by that is from the center to the crest, so this would be the crest, or from the center to the trough, this would be the trough. Right? So that's the amplitude, and the units here would be meters. So let's say units equals meters. Right? We always use meters. The next is frequency. Frequency is the distance. Let's go. I'm sorry. Wavelength. I'm getting ahead of myself. Wavelength is distance from one point to the same point on the next wave. And the units are meters as well. Now, we use the term lambda to refer to a wavelength, and that just looks like that. That's the lambda. It's a Greek letter. And so here is the wavelength, from the distance from one point to the same point on the next wave. So from here to here is a wavelength, from here to here is a wavelength, or from crest to crest is a wavelength, as you can see. Frequency is the number of waves that pass a point at a time. So it's and that time has been seconds. So you could think of it as oscillations per second, and the units are hertz. And that's just Hz. Okay? So remember, this is not standing still, it's moving. It's constantly moving, just like a wave on an ocean is moving. And if you had a timer and you waited for the time it took for one crest to the next crest, that would be the frequency. So as the wave peaks to peak 1, peak to peak 2, those are frequencies. All right. Now speed is the units. I'm doing units first this time. Units are meters per second. All electromagnetic, and those are the waves that we're going to be addressing. All electromagnetic. The light that we see is an electromagnetic wave, travel at 3 times 10 to the 8 meters per second. Now, sound is a mechanical wave, and it travels at 340 meters per second. That's why you can see lightning fall a lot sooner than you can hear it. Notice the inverse relationship. Notice the inverse relationship between frequency and wavelength. That's important. So as the wavelength goes up, the frequency goes down. So the time that it takes is a lot slower with a long, big wavelength. But with a short little wavelength, the frequency is very, 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 very fast. So as one goes up, the other goes down, and that's what we mean by an inverse relationship. All right. Now, visible light is part of a spectrum of energy called the electromagnetic spectrum. All right. Now, so let's address the electromagnetic spectrum. Here's the electromagnetic spectrum, and here are the waves that we were just introducing you to. And as you could see, non-ionizing harmless waves are radio waves, but wavelengths that are extremely short, high frequency, high energy wavelengths are ionizing. Those are harmful. This is just the little spectrum of the electromagnetic spectrum that we can actually see. This is the visible light spectrum, and as you can see, red is less energy because it has a longer wavelength, and the violet has the most energy because it has a shorter wavelength. Plants prefer light at this end of the spectrum because it has more energy. Now, what we're trying to do, don't forget, is we're trying to see the connection between light and the electron. Believe it or not, this guy named Planck was able to sort it all out. The Planck's quantum theory, matter can emit, or absorb, energy in little bits or little chunks called quanta. And the singular for quanta is quantum. Right? Now, this is also referred to as the photoelectric effect. That basically says that electrons are emitted when light shines on some types of metals. Not all, but some types of metals. All right, and so now it's starting to sound more like a particle, isn't it? So here is a particle, and then here is here's a photon. Here's a photon of light. Well, when they hit each other, then the electrons. This is a photon of light, and this is an element. When it hits it, electrons then are emitted. And what he found out was that the energy equals his constant, which is a very, very small number, 6.6 times 10 to the negative 32 joules, very, very small number, times the wavelength. His constant times wavelength equals energy. And so now what he's doing is he's making a connection between energy and waves. which was really wacky stuff at the time. Today it's a lot more well accepted. So a photon is a quanta of energy that is transported in light. So what's the relationship between frequency and light and energy of a photon? Is you could think of it as here we are, as I said before, this is the visible range. Violet, blue, green, this is the visible range of light. Yellow, orange, red. Well, here we have high frequency. Well, actually it's flipped, isn't it? This is low frequency here. No. I flipped it around. I shouldn't have done that from up here. As you can see, red is at this end, and violet is this, and so I flipped it, didn't I? And that's confusing. So this is high energy, and this is low energy. So energy is going in this direction for that visible range. So the frequency, so the relationship between frequency of light and energy is that if you have a higher frequency, here's high frequency, you have higher energy. If you have lower frequency, you have lower energy. So that's the relationship. So let's talk about some of these review questions that you see at the end of the chapter. What does it mean to say energy is quantized? Well, based on the energy level of the electrons, the amount of energy that matter absorbs is a quanta. So the amount of energy absorbed, absorbed by matter is a quanta. And that quanta really depends on the energy levels of the electrons. And we're going to talk more about that. How is energy of a quanta of radiant energy related to frequency? The greater the frequency, as we just said, of the electromagnetic spectrum, the greater the amount of energy. So higher the frequency, the greater the energy. Can you see? Can you see energy quantized? No, it's too small. Now we talked about how small it is because, as you can remember, Planck's constant is very small. Remember, joules per second. This is a very small number, so you can't see it. So it goes in steps, but because the steps are so small, you can't see it. So the short answer is no, you can't see it.